In example 2 from section 8.4, we see that our integral involves a component of the form square root of a squared plus x squared, where it's seemingly obvious that our a value would be a 3, since the a squared matches up here with the 9. And much like the previous example, we are going to have to perform another trigonometric substitution. And in this particular case, that substitution turns out to be x equals a times the tangent of theta. And once again, specific to this problem, where the a is 3, we would have x equals 3 times the tangent of theta. Now, as I said before, if you looked at example 1, there is sort of a rhyme and a reason as to why the tangent gets employed here. And it all sort of traces itself back to the right triangle with an angle measure of theta for one of the two non-right angles. And if this case, if this substitution truly is to work, then it's pretty clear that the tangent would be x divided by a if we divided the a over. So that would mean that the opposite side of the theta would be x, the adjacent side would be a. And upon performing a Pythagorean theorem here, the hypotenuse would have to be the square root of the sum of the squares of those two legs. In this case, the square root of a squared plus x squared. And that matches up with this form that we see present in the integral. So, as we said before, once we perform this substitution, we will physically take out the x in the problem and replace it with the 3 tangent theta, which in this case would give me 9 tangent squared of theta. Now we don't want to forget about the dx. The dx here is going to be substituted out as well once we take the derivative of this particular function. Derivative of 3 times the tangent of theta would be 3 times secant squared of theta, and then I'll just multiply my d theta over, and then that will essentially become my numerator now in this new integrand. And to perhaps slightly complicate matters a little bit, we notice that this was a definite integral problem with 3 and 0 as the boundaries. And if I go ahead and take care of those boundaries and write them in terms of theta, what that will allow us to do is to not have to back substitute the very end of the problem. So to take care of that, I'll once again revisit my equation here where x is 3 tangent of theta. I will go ahead and use 0 as my x value first. And if 0 is equal to 3 tangent of theta, that leads us to saying that the tangent of theta is 0, which of course gives us a result of theta equaling 0. So it's kind of interesting. The lower bound of 0 changes to a 0. Now I doubt that that's going to happen for this upper boundary. Let's go ahead and let x be 3. 3 would then equal 3 tangent of theta, which results into the tangent of theta being 1. And if we go ahead and figure out exactly what does that angle measure have to be so that the tangent ratio would be 1, well, that's simply a situation where the opposite side and the adjacent side are the same, and that only happens in a 45, 90 degree triangle or a pi over 4 degree measure. So we have our now upper bound of pi over 4. One thing that's going to be common to all of these types of problems is the special factoring that takes place here in this radical. You notice that you can pull out a square root of 9, and that square root of 9 ultimately will become a 3 out in front and will indeed cancel with the 3 that we have there in the numerator. So if we go ahead and take care of that, our integrand would now consist of a secant squared on top with the d theta, if we decide to go ahead and put it there. And then the denominator is now the square root of 1 plus tangent squared of theta. Perhaps you notice something sort of special about that denominator, 1 plus tangent squared of theta, in that it will become secant squared of theta by the Pythagorean identity. And then the fact that it's underneath a radical, the square root of secant squared will in essence just become a secant. So what does that say? Well, if you're, oops, I noticed I forgot my denominator 4. I don't want to do that. Make sure I get that upper bound correct. Pi over 4. Now getting back to what I was saying a moment ago, the square root of secant squared will become a secant, which will then do a little canceling with the secant squared up here in the numerator. And if you follow that okay, hopefully you see that I will have a integration of secant that has to be performed there. All of that simplification will lead us to a secant in our integrand. Do you know the integration of secant? Well, hopefully you do. It's a formula that was presented to you way back, I believe, in Chapter 5. It's not one of the prettier ones, that's for sure. The integration of secant is one of our special logarithmic forms. Turns out that it's the natural log of the absolute value of the secant plus the tangent. One way as a student back many years ago that I would always remember this, actually, let's get rid of this integration because we don't want that anymore, do we? We've actually taken the integral of this thing. So now we're ready for this sort of notation. But as I was saying there before I corrected the mistake, one of the things that I used to do as a student to remember that the integral of secant turned into this form was that the derivative of secant is secant times tangent. I just remembered that the integral of secant also possessed that secant and tangent component, but you're just sort of on your own to memorize the fact that you join those together with a plus sign instead of a multiplication, and the fact that they do reside in this natural logarithm. Now we will go ahead and evaluate this by plugging in our pi over 4 and our 0. So we would have the natural log of the secant of pi over 4 plus the tangent of pi over 4. And then that will be subtracting the natural log of the secant of 0 plus the tangent of 0. Now, to evaluate these, you might want to think of secant temporarily as 1 over the cosine. So, in essence, we're looking for the cosine of 45 degrees, which we could maybe rely on a triangle that I'm going to draw up here in the upper right-hand corner. Our normal 45-45 relationship would look something like this, as far as its basic ratios are concerned. And, of course, cosine is adjacent over hypotenuse. That would be 1 over radical 2. But by the time that that is sort of reciprocated, we would just get radical 2. The tangent of 45 degrees, opposite over adjacent, is 1 over 1, or just 1. Going to the secant of 0 here. Well, think of this as 1 over the cosine of 0. Best way to evaluate the cosine of 0 is thinking more about what the graph of cosine looks like. This would be a possible graph of cosine, and the cosine of 0 is obviously going to be a 1, so we have 1 over 1, which is 1. And then the tangent of 0, we kind of talked about this a little earlier when we were working with this step up here. The tangent of 0 would actually be 0. Or you could think of it possibly from the standpoint of the graph of tangent. Looks like this. Thus it goes through the origin. Now you'll notice in this second natural logarithm expression right here that the natural log of 1 is all that remains, which means we're going to get an ln of 1 or 0 in that case. So it's pretty much going to like disappear on us. And our final result would just be the natural log of the quantity radical 2 plus 1. Really don't have a need to put that in parentheses or absolute values anymore because it doesn't run the risk of being a negative answer. So we could just say the natural log of the quantity radical 2 plus 1. And if you took your TI Inspire calculator, you could easily check this by using the integration capabilities there.